to talk here. Sorry I couldn't be there in person, but it seems a lot of interesting discussion, a lot of interesting talks. So I'm going to talk to you today about what's called the LEXI project for Learned Exascale Computational Imaging, which is part of this Excalibur program that we heard about earlier this morning. So in particular, it's one of these kind of cross-cutting research projects within the Excalibur program. So I'm going to talk a little bit about the kind of background, the context and motivation for this work, why we're interested in exascale imaging problems, the kind of AI approach to tackle these type of problems, and then the computational strategies to be able to kind of do these things at the exascale. And then I'll finish with a few kind of initial results of some of the work that's in progress. Okay, so our main kind of canonical application that we're focusing on is the square kilometer array, something that maybe might be familiar for some people. The SKA is a huge kind of next generation radio interferometric telescope where we have hundreds or thousands of dishes and an antenna working together as one imaging device. So there's two SKA instruments which are actually have begun construction now, earlier this year, or maybe even earlier last year. Construction has begun. There's one based in South Africa, the SKA mid device, which has got a couple of hundred dishes basically, and then the other instrument is based in Australia, and there we've got hundreds of thousands of antenna. And these are essentially going to be, huge big data exascale type computing instruments. So for SKA mids, we get something like almost 9 terabits per second, and something similar for SKA low. And these telescopes don't, measure images directly. We need to do essentially computational imaging to recover images from the raw measurements made by the telescopes. So that's our kind of motivating application. I mean, I'm not really going to talk about science in this talk, but just to give you a flavor, there's a huge range of kind of science goals that SKA will address. Better understanding of dark energy, testing general relativity and the strong field limit, and a number of other things, exoplanets, another very topical example. So there's a huge range of really exciting new science we can do with these instruments, but actually getting images, getting reliable, accurate images that we understand the limitations as well out of these huge new instruments is really going to be a huge computational challenge. So as I said, with these kind of telescopes, we don't acquire images directly. What we actually acquire approximately are Fourier measurements. So we get a kind of sampling in the Fourier domain, and from that we need to recover an image. But we don't capture all of the information. It's a limited sampling in the Fourier domain. So we have a ill-posed inverse problem that we need to solve to be able to get images out of these telescopes. And we need to do this now at the exascale with these huge data sets that are going to be acquired. So this kind of interferometric imaging task is essentially now going to be an exascale computational inverse imaging problem. So that's our kind of canonical application. That's the kind of thing that we're focusing on in the LEXI project. But there's a lot of similarities with other imaging modalities as well. So we'll also be targeting optical interferometry, some kind of miniaturization type techniques. Yeah, there's a lot of similarity actually between interferometry and MRI imaging and medical imaging. And again, you get these kind of inverse imaging problems in seismic imaging and in computer graphics as well. So not all of these are necessarily exascale computing. SKA certainly will be, but the techniques that we can develop will be applied across these broad range of areas as well. So these ones that I've mentioned are ones we're specifically focusing on the LEXI project, but then there's a whole host of other applications kind of beyond these areas as well that, we're very keen to kind of collaborate with people and consider applications in other areas as well. We've got a large number of partners on the project, people heavily involved in the SKA itself, some of these other kind of imaging modalities as well. So, as I said at the beginning, this is essentially one of these cross-cutting research areas. We're tackling this from a variety of different angles. So obviously there's a large scientific computing and exascale HPC component, but then inside of that, we're also integrating machine learning, AI approaches, mathematical, statistical, and physics. So really trying to bring all these things together to tackle this exascale computational imaging problem. Just to mention briefly, we've got a reasonable sized team of a number of co-Is across both physics, maths, stats, scientific computing, and HPC. A number of research software engineers, and then also a number of postdocs and PhD students all working together on the project. So let me just mention briefly the traditional approach to solving these types of problems, which is really the kind of state of the art today, is what's called essentially variational regularization, where you solve some optimization problem. And you basically have some term that characterizes your data fidelity, how well you match the data, and another term that captures your kind of prior understanding of the types of images you might expect to see. So this is very much a kind of handcrafted approach. You have these handcrafted priors and some kind of model of the instrument and this data fidelity term. But here, clearly, there's no machine learning. You're not learning the types of priors you might expect from simulations or from existing observations. So with the Lexi project, we essentially taking a hybrid approach. So what I just discussed was a model-based approach. You have a model for your instrument, you have a model for your priors, which end up being handcrafted, and so maybe not the most tailored. On the other end of the spectrum, you could have a fully learned approach where you just throw machine learning at the problem, but in reality, that's not typically effective for these types of problems because they're seriously ill-posed. So what we're doing here is taking a hybrid approach where we do leverage machine learning. We learn kind of prior information from the data, but we also exploit knowledge of the instrument, of the telescope as well, and that helps stabilize the inverse problem. So we're trying to get the best of both of these alternatives. And yeah, kind of a naive application of just machine learning, throwing it at the problem is not necessarily going to work well. So this brings me to the computational strategy. As I mentioned, it's a kind of hybrid approach where there's deep learning components, but we also have some kind of model-based information as well and leverage that understanding of the telescope. So it's very much a big data problem. We've got huge data sets on the horizon from the SKA. It's very much a big compute problem. But here we're not actually considering big machine learning models or big deep learning models. And that's because, if we wanted to really train with the full telescope, this huge exascale problem where imaging once is really challenging, we can't necessarily do that computationally, when training deep machine learning models. So we have to think a bit more subtly about how we can tackle this. So some of the things we've been doing here are multi-scale telescope models where parts run at the full resolution, but parts run at sub-resolutions when embedded in these deep learning models, or training deep learning models that are actually agnostic to the telescope model. So your training now is based on just your images or the types of observations you'd expect, independent of the telescope. And then when you're actually doing inference, you combine information from the two. So in some sense, this can sometimes reverse the computational challenge of training and inference. We usually think of training as being the huge compute and inference being an execution of a model, which typically is just once, and so can be quite quick. It's different here though, because inference is a huge computational problem. So inference is really where the huge compute is, and we couldn't just do this lots of times in a training setting. So we have to think differently about the training, which actually means the training cost is often, by structuring things this way, lower than the inference cost. So we've been developing a number of computational paradigms to address this, or not. Or leveraging existing paradigms. Clearly we have to think carefully about how we partition the data. And actually we distribute not only the compute, but design the algorithms in such a way such that storage and memory is also distributed. And we really try and minimize the communication overheads between nodes in a large distributed system. We can also take account of stochastic approaches to distribute things where maybe we don't work with all of the data at once because there's just too much. And so we can work with subsets of the data, but in very particular ways, so we can guarantee at the end, we still get the same performance as if we had considered all of the data. And obviously we don't also only just want images out, we also want to have some understanding of their accuracy and the uncertainties in those images. And that is a huge computational problem. The kind of traditional approaches that would be applied to do that. So if you think, for example, like Monte Carlo methods or MCMC sampling, we just can't do that at the exascale for these types of instruments. So we have to think of alternative approaches to uncertainty quantification and how they can be highly parallelized and distributed. So let me just finish up by running through some initial results, and maybe I can make some of those general concepts a bit more concrete with some examples. So we've been considering this SPIDER instrument, which actually is an optical imaging device. And the idea here is miniaturization. So you can put essentially the telescopes that you put in space, they become 2D instead of 3D. So you don't have a 3D telescope with a large size. It's a 2D flat telescope, and you miniaturize the telescope, but now you need to essentially solve inverse problems to recover images. So this is not necessarily an exascale problem, but because it's a smaller scale problem, we can develop the underlying algorithms and explore how effective they are. And in a second, I'll come to then extending some of these things to things like the SKA. So here what we've done is basically, integrating the understanding of the instrument, of the telescope inside the machine learning model. So we need a differentiable implementation of the operator that models the instrument so that we can train. These plots here show reconstruction performance. So higher on the y-axis is better performance, and we have a distribution across a training and test set. The distributions for training and test set match fairly well, so we're kind of confident that we're not overfitting. And then we've got different methods on the x-axis. The kind of current state of the art is this primal dual approach, and we do as well as that with these machine learning models, or a little bit better. But really what we're targeting here, the most critical thing, is the speed of imaging. So this kind of traditional approach takes around a minute or so. Like I said, this is not exascale computing here, but takes a minute or so to make an image. We can reduce that now to 10 milliseconds, which opens up the possibility of real-time imaging for these kind of space telescopes. Here's some examples of recovered images. It's kind of summarized in the previous results, but just to show them. I'm not sure they necessarily come through so well in Zoom, but the key point is, we do just as well as the other methods, or maybe a bit better sometimes, but orders of magnitude faster. So now we've been extending these kind of approaches to work with radio interferometric telescopes like the SKA. The problem becomes more challenging here because now the observation, or the kind of operator that models the telescope, changes on an observation by observation basis, because it depends where the telescope is looking over the sky, if it's kind of tracking that source over time, the duration of the observation, the configuration of the telescope. So this makes the problem much more challenging. We can't just train once for a particular type of measurement operator. We need to be able to handle varying operators at inference time. So to do this, one thing we've been doing is integrating that knowledge of the measurement operator, or a kind of generalized understanding of it, into the deep learning model architecture. And this seems to be working very well. Same kind of plots as we had before. Obviously the best thing was if we could just train once with full knowledge of the telescope. So that's the full knowledge case. That's the kind of best case scenario that we can compare to. So we don't expect to be able to do as well as that because we don't have the full knowledge of the telescope and these settings, because it's changing. But nevertheless, with just the generalized model, we get fairly close to that, and then we can do a final amount of fine tuning. We get almost as good performance as if we did know that full operator. So again, here's just an image where we have the dirty image, which is the kind of naive reconstruction, and then we see the quality. Again, not sure it comes through so well, but we're getting almost as good as having the full knowledge of the operator. As I said, we also want to quantify the uncertainty in our images, not just make nice images, but also be able to understand, is what we're seeing really, is it really there or not? And where are the areas of large uncertainty in our image? But we do want to exploit data-driven priors, so deep learning models that learn effectively generative models of the types of images we'd like to see. But if we want to be able to do this uncertainty quantification at exascale, really high dimensional, high compute settings, we need more structure in the problem. So what we've done here is we learn essentially a generative model, but we've constrained it to be convex. And because of the convexity of the model, it actually opens up a lot of uncertainty quantification. There's a lot of nice results there that we can leverage. So the fact that we're using a data-driven prior increases the imaging quality significantly. Again, it's pretty hard to see probably on Zoom visually the differences in the image, but we have a signal to noise ratio of around 27 dB for the traditional methods, and we're getting almost up to 33 dB. So quite a significant improvement, but critically done in such a way that we can do this uncertainty quantification at high dimensions. So here's an example of that. We've got the reconstructed image, and then we have some kind of characterizations of the uncertainties at a local scale. So the alternative plots I'm showing here are not really showing exactly the same thing for our kind of LCIs or local credible intervals. It's not quite the same quantity as a standard deviation on pixels, but nevertheless, it gives you visually a kind of understanding of where large uncertainties occur in your image. And also, in this case, it relates very much to where there's large signal energy. But the key thing is this now we can do at the exascale. We get many orders of magnitude in saving in compute time to do this, where MCMC approach is just not feasible. And then the other thing we can do is hypothesis testing to see if, is structure in the image really there? Is it really physical? So one thing you might like to do, there might be kind of sources or, objects within the image, and you want to know, does that exist in the sky, or is that an artifact of the imaging process? There's some relatively simple examples here just to demonstrate it, but we can see, that blob on the bottom left, is that really there? We can do hypothesis testing, for exascale type data sets, and say in this case, yes, that blob was necessary. It's physical. We can also do things like try and study the substructure of images. So we can kind of remove some of that substructure and see if if our resulting image still fits the data model essentially. And again, we can say in this case, we really needed that substructure. That's really physical. That's not an artifact of the imaging pipeline. So finally, I'll just mention that we've got, we're prototyping these things at low resolution initially, but we've already made a lot of progress on these C++ codes that implement these kind of methods at very high resolutions. These are kind of ongoing development efforts, but it's all open source and available now already. So if people are interested, there's codes there that are tailored to interferometric imaging, but also the kind of general underlying techniques as well. And yeah, we're very, these are still under development with some of these new methodologies coming into them. The next step is now to apply them, on some of the Excalibur computing platforms and really benchmark them at, running at really large sizes. So I'll finish there and happy to answer any questions.
Thank you very much, Jason. So have we got one or two questions for Jason? Paul.
Mark, you must be itching to say something. It's your field almost. Hey, Jason, that's really, really interesting. It's Paul Kaleja from Cambridge. So that's running on GPU.